Okay. Okay, so can I begin? Okay, so hello everyone. So just in case like there are some new members in the group, so yeah, my name is Ismael De Paiva. I was a student, a PhD student at Chapman University, but last year I came to Israel, so I'm in Dr. Eliyahu Cohen's group now. And yeah, we have been working in this past year with quantum clocks. And yeah, I will talk to you guys about the result that like part of it we have on archive, and now I will show also a couple of slides with some new developments. So yeah, this work I developed with Eliyahu Cohen and also with Augusto Lobo, who used to be my advisor back in Brazil. Okay. Yeah, so first I'll just make an introduction to the subject we initially wanted to study, and also the framework I used for that. So I will talk about energy measurements and the existence of a certain type of time-energy uncertainty relation. And as we see, we got some non-unitarity in some special situations, so I will discuss a bit about it. And please, if you have questions, just ask me. I guess it's better than just wait until the end. So it's better if you ask in the middle, just so we can move together. But yeah, so I was interested in studying time-energy uncertainty relations. And the time-energy uncertainty relations, they are a special class of uncertainty relations because typically we talk about these relations for a pair of observables. And this is not the case for time, of course, but also this pair of observables, they are associated with two properties of the system. While time energy, you have the energy, which is a property of the system, and time, which is a variable of a clock, which is so something from a different system. So yeah, it's a special type of relation, and there are many different approaches for them. You can, for instance, discuss like, oh, how much uncertainty you add to a system during its evolution in a certain period of time. You can discuss it in a lot of different directions. The direction I was interested in is the one concerned with this question. Is there a minimum duration for energy measurements with a certain precision? So yeah, so you want to do an energy measurement and there is a minimum precision you want to achieve. Can you do this measurement arbitrarily fast, or is there a minimum duration imposed, fundamentally imposed by quantum mechanics? So first I'll just give a historical overview quickly, just to show the developments. And it started with Landau and De Paiva. This citation here is the original article, but you can also find this model in Landau's book of quantum mechanics. And the idea is like they consider their system a model for the measurement of energy. They were actually talking about measurements of momentum, and from the measurement of momentum, they would infer about the energy of the system. And in studying this model, they concluded that, yeah, if you want to achieve some precision, you cannot perform this measurement arbitrarily fast. There is some minimum duration for the experiment. However, later, Aharonov and Bon, they restudied the same scenario, the same type of measurement, and they observed that actually the model they presented was not the optimal one, and it would be possible to introduce a better model, and in this model you could perform the measurement arbitrarily fast. The article also, as far as I'm concerned, as far as I know, it's like it was the first one to introduce a time operator after Pauli's objection to the introduction of a time operator. But then, together with Popescu and Massar, he also added a new ingredient to this study. That is like, oh, still most measurements we perform in the lab, they take some time. Why is that? And it's typically because we don't know the Hamiltonian. If you don't know the Hamiltonian, you need some time to estimate it, but once you estimate the Hamiltonian, you can do the measurement arbitrarily fast. Another subtlety that we have in this problem is that until in these three first results, the discussion was based on a measurement performed by an external system. But what if a subpart of a system is measuring the energy of the rest of it? But then Popescu and Massar, they showed that if you consider the internal clock of the system, in that internal clock, the measurement can also be performed arbitrarily fast. So just to summarize this discussion, because we can have like the measurements being carried out by an external system or by an internal one, we might want to optimize to the external time or an internal time, and you might know and you might not know the Hamiltonian. And in these 8 possibilities, with the results I just discussed, we know the solution for 3 of them, 3 cases. And in this work, I focused on cases we know the Hamiltonian, and I wanted to understand, to try to unify this approach and also to understand what happens in the other scenarios. For that, we used the Page and Wootters formalism. But before I talk about the Page and Wootters formalism, I will briefly mention some basic, basic idea of quantum frames, because I believe it to be helpful. So suppose I want to say, like, I have 2 particles. I know that one particle is well localized in a certain position. The other particle is actually in a superposition between, it could have been in one of 2 precise points. When we say it, like when we have introduction to quantum mechanics, we just are introduced to these wave functions, but to write it in the first place, we need a system of reference. And the system of reference, they are physical systems. So this is actually written with respect to some system C. But then if I was like describing this from the perspective of system C, I could also switch my frame. I could, for instance, go to the frame of A. And then the frame of A, I can talk about, then I can describe the position of C, which has some distance to A. And then I can also talk about the state of B. Now, I can also, of course, go to the frame of B. In this case, the distance between B and C is not quite well defined. But because B can be in a superposition, then the distance between them is a bit undefined because of the superposition. So the description of system C will be a superposition. And the same is true for system A. But it's not, but observe that the distance between system A and system C is fixed. So the system C and A, they will actually be entangled if you switch to this frame, because or we get the first pair or we get the second pair with a measurement, because the distance is fixed. And more generally, then we can have a Hilbert space, a large Hilbert space that includes A, B, and C. And then this, if you take this system, the 3 systems, they should satisfy a certain constraint, which will give this relational conditions between the systems, which is what tells us, for instance, that the distance between system A and C is fixed, and it tells us that it's not quite well defined, the distance between A and B and C and B. So we do have a big constraint. Right now, this last part, I know it's a bit abstract, but I think with Page and Wootters, it will be a bit more clear. But this is just a basic picture of quantum frames that I want to give before I go to Page and Wootters. So in the Page and Wootters formalism, first we start with an isolated system. And if you have an isolated system, this system will satisfy the Wheeler-DeWitt equation, which is this equation there, Hamiltonian acting on the wave function is 0. This equation might seem a bit weird, but it, in a sense, is just the time-independent Schrodinger equation. We can always shift the 0 of the energy, so you can always say that the total energy is 0. You can always add a constant to the Hamiltonian, if you will. And this, in a sense, is a type of constraint. It's a constraint that Hamiltonian equations are imposed if you try to create a gravitational formulation for systems, a Hamiltonian formulation for gravity. And it's related to the problem of time in quantum gravity even, because if there is no evolution, how do we recover the usual notion of time evolution? And that's when Page and Wootters enter, because they proposed splitting the system in a part that would be a clock and the rest of the system. The clock, it has a variable time and a variable of energy, HA. And they don't need to be canonical, they don't need to be, I don't need to have the pair like position and momentum. In a sense, I can create a POVM for time, but in this work, just for simplicity, you consider that the variable of time and the energy of the clock, they behave just like position and momentum. So they satisfy the canonical relation conditions, and the eigenstate of time, it's like when you do the shift of, you apply the Hamiltonian, you always go to an eigenstate of time. This, of course, makes the Hamiltonian of the clock being abandoned from below, which shows that this is not realistic. Of course, this is an ideal clock, but it's still an approximation of clocks in some circumstances. For instance, if you imagine a clock that is given by the angular momentum, so the Hamiltonian is proportional to the angular momentum, and if you start taking the dimension of the space to go to infinite, you start approaching this ideal case. There are also other scenarios, but I want to discuss here because I don't want to start getting lost in this part. But just for simplicity, I assume an ideal clock. Then the total Hamiltonian, I write as HA, which is the Hamiltonian of the clock, HR, which is the Hamiltonian of the rest of the system, and what I'm calling H int TA, which is just a time-dependent portion of the Hamiltonian for system R. So, but time will be given by the variable of time in clock A. So with an equation like that, I can do now what we say, because right now, in principle, we don't have any perspective, it's just the entire system. So this is called a perspective neutral. But then I can go to the frame of clock A and start talking about the physical situation, physical scenario from the perspective of clock A, which corresponds to this projection in an eigenstate of time, dA. And when I do it, so first, like the action of HA in an eigenstate of TA, of time, is this time derivative. And then I can just recover Schrödinger's equation. So in this sense, this is a way to see, like, it's a solution to the problem of time in quantum gravity, in this sense that we can recover the usual dynamics if you have a system, part of the system working as a clock. More generally, yeah, so before I move on, this part is important because this is what I'll be using throughout the work. every time I do this procedure, I have the entire Hamiltonian that satisfies the Wheeler-DeWitt equation. I do the projection against the rate of time, and then I have the Schrödinger equation. From the Schrödinger equation, I can get an effective Hamiltonian from the perspective of the clock. And because this process will be repeated over and over, I will only go from the main Hamiltonian to the effective one. Otherwise it will be too repetitive. But more generally, also we can consider multiple clocks. So system R can be composed of a clock and another system. And then with that, we can obtain two effective Hamiltonians from the perspective of clock A and from the perspective of clock B. And just a comment here, if we have an event that's localized in clock A, it will typically have some uncertainty from the perspective of clock B. Okay, any questions so far? No? Okay, so then I will talk about the problem I was approaching, which is of energy measurement. And first I will study when an external system is measured. So I will consider an external apparatus that will be connected to the external clock, clock A, and I want to do the measurement of system R. But system R contains clock B and system S. So I can write a von Neumann Hamiltonian, this von Neumann interaction. And then the total Hamiltonian is this one, HA plus HR plus the von Neumann interaction. And then I can obtain the effective Hamiltonian. And the effective Hamiltonian is, if you see here, is just the usual one, which kind of makes sense because we have an external clock. So we just go back to the usual picture. But the interesting part here is that I can study the evolution of the operator TB, of the time of clock B, just using Heisenberg's equation. And by studying this evolution, I can see that the flow of time is the same in both clocks outside the measurement, not doing the measurement, but then doing the measurement, this flow changes. And it changes according to the function, the measurement function G, and the momentum of the pointer. Yeah, so, and also I can integrate this equation if I say that the measurement starts at TA equals 0 and the ends at TA equals tau. And if I say that the integral of G is K, so I will obtain this equality. Now, there are some arguments here. I will simplify a bit the discussion, so I will just refer to Aharonov and Bohn's result that the external time can be minimized. So according in the external clock, the measurement can be performed as fast as one wishes. So this means that tau can be as small as one wishes, but however, the average duration of a measurement in the internal clock will still be bounded by this quantity, by K times the expected value of P. So in general, we will have then some constraint. In general scenarios, we have a constraint for the duration of the measurement in the internal clock. So this is what I'm calling a time energy uncertainty relation, in that sense that I discussed before. And just to mention it again, there are multiple meanings to time uncertainty relations, time energy uncertainty relations. This is just this particular one, in this particular approach. Now, I was studying everything from the perspective of clock A, but we can also study it from the perspective of clock B. However, if you see here, because of the lack of commutativity between TA and HA, in general, this Hamiltonian is non-Hermitian. And this is not something, of course, this is not something I was expecting. It was just a result that it's still a bit of a puzzle, but I'm trying to understand it better. But if you will, just for consistency, we kind of see that the evolution of TA gives me the inverse of what I got before, which seems to have some consistency there. Now, if I study the measurements carried out by an internal part, so you have an apparatus, you see the apparatus is outside the system, but it's just because I don't want to start changing the labels. I can still say that one part of system R is the apparatus, but then I would have to start relabeling things. That's why I just drew it outside. But because the apparatus is part of the internal system, it will be using the internal clock as a reference. And then the external clock will be the clock A, will be just there sitting outside without interacting. In this case, the von Neumann Hamiltonian is written in terms of TB, but because of the lack of commutativity between TB and HB, the von Neumann interaction has to be symmetrized. And then, yeah, I can write again the total Hamiltonian, and I can write the effective Hamiltonian from the perspective of clock A. And then you see it's a bit different, but maybe not that different from what we expect. And if I study the evolution of TB, I get something a bit similar. Here, however, I didn't show details, but we concluded that there is no uncertainty, time-energy uncertainty relation. The reason, the simplest way I can explain it is maybe by saying that in the internal clock, the experiment can be performed as fast as one wants, as showed by Popescu and Massar. And typically, in average, the experiment will be shorter in the external clock. So basically, that's why we want to get any time-energy uncertainty relation. But again, if I study things from the perspective of clock B, I get a non-Hermitian Hamiltonian, this time because of the term with the imaginary unit. So it's again non-Hermitian, and okay, just for consistency, I can show this equation here too. Okay, so in a sense, when I started this work, this is basically what I wanted to study, and just to summarize this first part of the result. So if an external system is performing the measurement, the beginning and the end of the experiment will be very well-defined events because it's given in clock A, so it will be well-defined events in clock A. In clock B, there you have some uncertainty. However, in average, it will be longer, typically in clock B. And we found a time-energy uncertainty relation. When an internal system is measuring, we have a well-defined beginning and end of the measurement. In clock B, we have uncertainty in clock A, however, in average, the measurement tends to be shorter in clock A. And then, like, going back to the original table that we had initially, the answers would be yes for one scenario and no for the other. But then we have the question of the non-unitarity. And this is actually something that in the work that I just presented, I initially just had some speculation about it, like maybe it be somehow related to some decoherence effect because the energy of the clock is being measured. So I don't know. I had just some speculations. It was not very clear to me. And then, so in general, my impression was like, oh, maybe it's somehow the clock B will be a non-inertial frame. That's why the evolution in that frame is non-unitary. And now I'm trying to formalize it a bit better. So for that, what I start doing is like, first, if I consider the Hamiltonian of a free particle, I'll just call it H. I want to know how this Hamiltonian will be changed if the particle starts accelerating. So if the particle starts accelerating, I'm assuming that the particle will move only in a single direction, because then I can basically make acceleration a function of the position. In each position, I will know the acceleration of the system. That's why I will say it's moving in a single direction. And then I can write, I will basically just add a potential to the Hamiltonian. And the potential I'm just writing as m plus a function of the position then, that will be related to the integral of the acceleration. So this is the Hamiltonian, but I want to use the relativistic correction of mass energy for mass energy equivalence. So if m is just the rest mass, the mass should be updated by the energy of the system, should be added to the energy of the system should be added to the mass. And then in general, I will have this, the Hamiltonian will go to something, the total Hamiltonian will be the initial Hamiltonian plus 1/2 of this term. And I wrote in this way because there might be some terms that don't commute in general. And then what I want is to consider a system that is a particle m that has a clock as an internal degree of freedom. So m gives me the external degree of freedom of the particle. So hm here is just like p squared over 2m, just the kinetic energy, and then the Hamiltonian of the system. And in a situation like that, we do get a Hamiltonian that is typically non-Hermitian. So it was already like, oh, that's interesting. It seems I can connect the non-unitarity with the non-Hermitian Hamiltonians. However, I mean, this Hamiltonian is still a bit different from the previous one we found. So just to show that I can actually connect the previous Hamiltonian too, I will just do some modifications. First here, I will consider more than one system. So I will have two particles, and the only particle m is accelerating. Particle n continues not being accelerated, and particle n has a clock b. So that's how the total Hamiltonian will be in this case. Okay, so this, and then if I approximate, if I say that particle m is very massive, there is some situations I can approximate the Hamiltonian as proportional to the momentum. I wanted to put proportional here, but still I can put the constant as one, just for simplicity here. And in this case, the commutator between f of x and hm, it will be proportional to the derivative of f, and also the Heisenberg evolution of xm is just the identity. So basically, xm and the TA, they will grow like in the same way. The only difference is the initial uncertainty associated with xm, the difference between them. So in a sense, I can replace xm with TA, given that, I mean, of course, I have to keep in mind that I'm losing some information about the uncertainty in this step. But still, if I do this change, I can rewrite the effective Hamiltonian in this way. And if you see here, I disappeared with hm and hn, just because they would be two terms added here. And I can say like, oh, for simplicity, I'm not taking into consideration the external degrees of freedom in my study. So at least formally, I can recover that Hamiltonian for the time energy that's non-Hermitian, and I can connect with a system being non-inertial. Yeah. So any questions about this part?
Maybe I can ask a question. Although, let's see if I can stop the echo here. Is that better? Yeah. The question is it, so we know how to deal with, I mean, relativistic quantum mechanics in the presence, for example, if we want to construct field theory, we have a well-formulated theory of relativistic quantum mechanics, and that's entirely a unitary theory. So my question is, why do you have this kind of analysis in terms of adding acceleration, having some relativistic correction, and somehow you get non-unitarity out of it? That seems to go against our best understanding of how to deal with relativistic quantum mechanics.
Yeah, I mean, but acceleration is also like, if I use the equivalence principle, it will be, I can also say that it's a gravitational effect in a sense. And a lot of people expect some form of non-unitarity in gravitational theories, right? In gravitational quantum theories. Of course, this non-unitarity will be like more prominent next to black holes or things like that. But the way I see now, because of this result, is that like, oh, in a sense it's there, but it's very small. But once you start getting to these scenarios, because I mean, you can't escape gravity, so you don't have a system that's completely inertial, that is 100% inertial. So it's there, but it's very small. But the more your system becomes non-inertial, the more this non-unitary started being preeminent. So that's more or less my view. I don't know if it makes much sense. Maybe this is still a bit speculative, I know, but do you have comments?
I do, but perhaps we can go to the next question, or we can continue with the talk.
Okay, no, because I mean, I'm almost ending here, because I want just to call attention by something that when I wrote not stuff related to this part, but the time energy uncertainty relation, most of my analysis was based on the system, on what I saw from the perspective of clock A. So clock A gives me a unitary, so it's fine. However, I did use analysis from the evolution from the perspective of clock B, just to kind of show some type of consistency across the two perspectives. The problem is, when I did it, I used the Heisenberg picture. And the Heisenberg picture, it's a detail that I had escaped, and also I showed the manuscript to a lot of people, at least one referee got it like, how you need to give some justification to use the Heisenberg picture. And the reason is, shown again in Heisenberg, they will be equivalent, they are unitarily equivalent. And if I have a non-Hermitian Hamiltonian, in general, the unitary will be, the evolution will be non-unitary. And we can see this from the expected value here. So it becomes non-linear in psi if the norm of psi is changing time. And then if you try to get the equations of motion, you'll see that you can't really just say that switch like from the states evolving time to the operator evolving time. It becomes more complicated. So this was a bit of a challenge, but a bit by accident. I found that Dirac invented a method to deal with non-Hermitian Hamiltonians. And most importantly, maybe like 1 year later, Pauli wrote about it, and Pauli's article, I think it was very clear, it was very helpful for me. And in this method, we introduced a new metric, eta. This metric is Hermitian, and its eigenvalues are -1 and 1. That's the only possible type of eigenvalues that this metric will have. But as I said, it's one possibility, it's -1, so it's an indefinite metric in general. And this metric will be associated with an inner product that I'm writing this way just to still keep some, and this metric is an operator, Hermitian, as I mentioned, just to keep a connection with the original inner product, I'm writing this way. And the problem with this, so I'll just move on and then I'll explain a bit the problem with this approach. And then, but okay, if I have a new metric, I can also introduce a new conjugation. The conjugation will be in this way, and physical quantities should be self-adjoint with respect to this conjugation. And they are called like eta pseudo-adjoints in this case. Then I can compute because physical quantities are self-adjoint in this sense, the eigenvalues of the Hamiltonian will be real in this sense. And then I won't have the problem of the norm changing time. And then, yeah, so I can compute the expected value just using this product like in the usual way in a sense, just with the metric, the new metric. And then it holds that I can write the evolution of the expected value in this form. So I can go to the Heisenberg picture. The problem with this approach is that because T to the metric is indefinite, it has ghost states. It has states with negative norm, which seems, I mean, to me, it seems something very weird, but someone was telling me that in some field theory approaches, there are ghost particles, so maybe there is a way to think about how to deal with them. And the most known example of something that you can say that fits in this approach is the PT symmetric Hamiltonians. If you consider the PT metric, it gives you some states with negative norm. However, it was shown that if they have unbroken PT symmetry, they have a third hidden symmetry, and you can, with consider this new symmetry, like so the three symmetry PT and the new one, we can get a metric that's positive definite. So the states that were before had negative norm, they start having a positive norm again. Yeah, so this is something that I'm trying to understand also, like how, so my idea at the moment would be like, okay, if this is the correct approach, typically eta is just the identity, and maybe some deviation from the identity would tell me about the inertial character of the frame. Yeah, I'm trying to understand it a bit better. It's still kind of new, and in a sense I wanted to present actually to see what people say and to get some feedback just to see what people think of it. So basically that's what I want to say. Like the first part, when I talked about the energy measurements, they are in this first manuscript. I'm also advertising a second manuscript that where we study the modular energy of quantum clocks. Yeah, so that's it. Thank you.
Okay, thank you very much. Thank you for the great talk. It's very interesting. Lots of things to think about in terms of the different different clocks. That was very fascinating. Questions from the Zoom audience.
I haven't got anything. So Andrew, did we actually end up forgetting to record after all?
No, I'm recording.
You are? Oh, excellent. Okay.
Questions?
Oh, I see it now.
So I wanted to go back, if there are no immediate questions from the Zoom, you guys think about what you want to ask about. Let me ask another question. So I'm going to come back to my issue about non-unitarity. So in special, so you appealed to the equivalence principle to talk about gravity. And indeed, if you throw gravity into this mix, things become strange. But in terms of acceleration, though, so special relativity is perfectly able to describe acceleration. And non-relativistic quantum mechanics is also perfectly capable of describing acceleration. So I fail to see how just simply introducing acceleration would introduce non-unitarity in this picture. And I guess does it come back to the issue that you're trying to describe the time dynamics from this internal point of view, that things become ill-defined in some sense? Or what is your view of this?
Yeah, so I think the difference from the usual approaches is that we really consider the coupling between the internal degree of freedom of the system with the external degree of freedom. If you don't consider this coupling, so if you do like a semi-classical approach where like instead of putting H here, like in this, can you see this, the arrow here? Let me see, maybe if I use this.
Yeah, no, I see. I can see. Yeah.
Okay. Yeah. So if you do a semi-classical approach instead of H, here we would have the expected value of H, for instance.
Yeah.
In this case, we don't get a coupling between the internal degree of freedom and the external, and we would see unitary evolution. So, I mean, in the case I'm describing, I'm working mostly with systems like with low energy. So this would be a very small effect, but my impression is that they will be there. I can't find a mistake. I mean, in a sense, I'm presenting, talking to people to see if I find a mistake in this approach, trying to understand it better. But my impression is that because of this coupling, we get this non-unitarity.
And here, I suppose it just comes from the fact that this operator f of xm doesn't commute with the Hamiltonian. Is that right?
Yes.
Yeah. So could I also view it from the fact that I'm just trying to describe a subsystem, but using only the operators from the subsystem and not from the external degrees of freedom?
Yes.
Yeah. So it would seem to me that that's a sort of a generic phenomenon.
Yeah, I mean, yeah. So I think to be generic, because imagine a quantum clock to always be part of a system, and this system like to be inertial up to some order. So the bigger this order, the closer to a unitary evolution we will have. Yeah. But I think I don't know. Maybe they're imagining someone just to actually design the clocks. Maybe the person has to do some adjustments from a unitary view. I don't know, just to correct the errors due to the non-unitary caused by this coupling.
Okay.
With the system, I don't know if do you see? So yeah, my impression is that it's generic because of it. I mean, imagine in Page and Wootters, it's the entire universe. We have some systems we use as a clock. Yeah, my impression, sometimes when I'm discussing here with the group here, I just say, it seems to me that there is no escape. Unless there is some mistake I'm making somewhere, but it seems there is no escape from this.
I have a sort of question maybe that relates to this. So have you ever considered trying to do the analysis of the clocks kind of in the same way that you do when you're deriving special relativity, where you are always keeping track of a late signal passing between one system and the other? I'm wondering if adding in relativistic delays would give you a kind of a more nuanced picture of what's going on here.
Yeah, this is like, I want to at some point to have like a physical model for a clock, instead of just saying like, oh, I have the system that's the clock, I will actually say like, oh, the system is oscillating in this way, and just to have a toy model, a very simple system, just going up and down maybe or something like that, and to see what happens.
Yeah, I guess what's different, normally we're talking about, we define like a light clock just by having a light signal bouncing back and forth between two mirrors, but here you would also have something where you have signals being exchanged between your two systems. And so that might introduce an entirely different complication.
But is it for synchronization? Because it seems more like a protocol for synchronization, right?
Well, I'm just thinking about how you end up deriving like the space-time interval and the relativistic metric. You're always having to take these extra delays into account. So it's just, I think it might add an interesting complication to the problem that maybe would open up some new questions you could ask.
Okay. Yeah, because I've seen this type of protocol exchanging signal for you to synchronize clocks. So if you keep sending the signal, of course, once the clocks start, they are not synchronized anymore, you'll be able to see, like if you expect to get signal from one, then from the other, and intercalate in this way, once you get two signals from one, you know, now they are not synchronized anymore.
Yeah, but you would also end up with like a superposition of whether or not you think the clock has ticked based on where you are when you observe it. If you're observing the signal from the clock and you're in a superposition, that would change maybe the time that you ascribe to it. I don't know. It just seems like there could be some additional details to think about there.
Yeah, I think, I mean, I don't know, I'm talking about it. Next month, I'm going to Vienna and I will discuss it with Chaslev group. Yeah, I'm trying to see if there is a mistake, I want to find it. If not, I believe there is a lot to study to understand these things better. So it will be something, there will be a lot of works on it. Yeah.
Okay, any other last questions?
I have a small question.
Oh, yes, go ahead, Tathagat.
Yeah, I missed up. You introduced this metric towards the end. I missed the physical significance of this metric.
Yeah, I mean, to be honest, this approach with this metric, I found out about it maybe last week or 2 weeks ago. And even with PTC metric systems, I'm not very familiar. So I'm started separating some articles now. I don't know if it's just a way for you to correctly compute the expected values. So like, oh, you know that once you use this metric, you compute the expected value, it will give you what you actually measure, or if it actually has a more, if it has a deeper meaning associated to it, an operational sense. It's not clear to me. Maybe someone here is more familiar with PTC metric, because even though my system they won't always be PTC metric, I think it's a good way to start studying, because there are a lot of studies about PTC metrics. Do you know, Andrew?
Well, yes. I mean, there are lots of discussions of symmetries in quantum mechanics. And so this is what it was reminding me of. But it sounds like something, you're talking about something deeper here. So like you change the linear structure of the Hilbert space into some kind of curved structure. That's what it seemed to me you were talking about. Is that right?
Yeah. Well, I think so, because but see, even if you see, even PTC symmetric systems, in a sense, that's what they do too, right? Because they have this, the new metric is given in terms of these reflections, like spatial and time reflections. So they also tells you about some symmetries, spatial symmetries you have in your Hilbert space. I think the same will be true in this case. Now I want to understand, like, oh, if they are actually connected to, if I can read the state of the frame from them, I need to understand better how I can read, how much information I can get about the frame just by looking at the metric. But my question is like, relate to what he was asking, is like, for PT symmetric systems, is there an operational meaning for the PT metric? I say, or maybe it's just a way to compute the correct expected values, right? my guess. If you don't use it, you don't get the correct expected values once you do the experiment. That's my guess, right?
Okay, why don't we thank Ismael again for this very interesting talk, and yes, good, and we'll see you all next time.
Yeah, and also we can discuss later, like since you are studying quantum clocks, I'm trying to see different perspectives and
Yeah.
looking for other problems.
I missed, tell me again where you are right now.
I'm at Bar-Ilan University. It's in Israel, very close to Tel Aviv.
Okay, very good. All right. So you can talk with these Israeli guys, right? Talk to Lev and Yakir and people like that. So
yeah, if it was not the pandemic, it would be easier. But Yakir I still see sometimes, and in this new direction we are going now, he's even participating. But I didn't show him this part of the metric yet. But
okay.
he is participating in this connection with acceleration.
Okay. All right. Thanks again. We enjoyed the talk.
Thanks, everyone.
See you. Bye-bye.